will be due Thursday, but we've got plenty of time to get through this booklet. All right, here are two terms. They're both a measure of how length varies with respect to time, per second, per hour. However, one is a scalar quantity, it doesn't care about direction, and one is a vector quantity, and it needs a direction. Now, here's the tricky thing. They both have the same symbol. So just underneath, could you write here, they both have the same symbol, which is V, lowercase v, and they both have the same units, which is meters per second. Okay? And they both have the same equation. We're going to write an equation. There is our equation. Okay? Now, obviously, time is common for both. So we're going to go T is time. Have it in seconds. Now, S is the symbol for distance, or it can also be the symbol for displacement. And they both are measured in the same unit, which is the meter. Okay? Which means our V, if we're using distance, V is going to stand for speed. Or if we use displacement, it's going to stand for velocity. Okay? Now, you may have seen this magical, wonderful triangle if you've done maths and it helps you sort of rearrange. Has anyone seen the triangle? I might have shown you in year 9 as well. We can chuck in our magical, wonderful triangle. V equals S over T. Who remembers the thumb? Good times. Here's the thumb. Yeah, hang on. Here it is. Okay. And basically, what? If you want to figure out your equation, you put your thumb over the variable you want, and that gives you S over T. If we wanted to rearrange for S, we're going to put our thumb over S, and what's the equation now? V times T. So let's just write that down over here. S equals VT. And then lastly, if we wanted to solve for time, we cover T, and what's the equation? S over V. Okay? So just remember that you can scribble down the triangle. Some math teachers don't like teaching it because it's not really teaching you the proper rearranging of equations. But if you set up your equation, we can rearrange for our 3 variables. So it's going to be very common throughout this 12 weeks. You'll be given 2 variables and asked to solve for the third. Because there might be 3 variables, we've now got 3 different equations for those variables as the subject of the equation. I just realized I didn't put down the units for velocity and speed. They are meters per second. Now, just on that, you could write it ms to the negative 1. You could also write it as m/s. You could also write it as m times 1 on s. You could also write it as ms to the negative 1. They all represent the same thing. It's the units of mass divided by the units of time. Okay? I would like you to start using this little subscript, or superscript, negative 1. Alright, so we're not going to write m/s, you're going to write ms to the negative 1. And Brendan, could you close the laptop? Sam, close the iPad. Bond, iPad. Angus, iPad. Close them all, you don't need them. So, remember, if it depends what you're given. If you're given a direction, then boom, you're promoted to the vector quantities, displacement, velocity. If you're only given a scalar, then you're in the blue. You've got distance, you've got speed. but they do represent different things. So let's look at this example here. Okay? So here's a student, and he's going to run. And by the way, this could be, let's just say he's running around the oval. So he runs to the end. He then turns around. Could we just write, we haven't got a time yet, could we just write next to this, and he does it in 150 seconds? Obviously, for us to figure out his speed and velocity, we need to know how fast he does it. All right. Now, we don't need to, but we could draw in a very simple vector diagram. 100 meters north, 300 west, 100 south, and we should be able to see that the resultant vector is 300 meters west. Well, obviously, that's going to be his distance. Remember his distance? You ignore the direction. He ran 100 meters. He ran 300 meters. He ran 100 meters. How many meters has he run? 500. So we're going to write that down. 100 plus 300 plus 100. Now that is a scalar. Okay? But it's going to be, in fact, it's S equals. Remember, the symbol for distance is the same as displacement. But then the other one, obviously, you've got to use our vector additions because the vectors are important. How far has he displaced himself and in what direction? He's displaced himself 300 meters west. Okay? So we've got two different S values. So his speed, we're going to use the same, V equals S over T. We're going to go 500 meters over 150 seconds gives 3.33 meters per second. That's his speed. Try and draw that a little bit nicer. Okay? But his velocity, same equation, V equals S over T, but it's going to be displacement over time. This one was distance over time. So we take the displacement, we're going to go 300 meters west divided by 150 seconds. That gives us 2 meters per second. The west comes along for the ride, and that is your velocity. Okay? So, very simple set of instructions, but we've got the scalar representation, we've got the vector representation. Okay? Now, one way to try and think of this is imagine you were in PE and your PE teacher tells all the boys to go off for a run around the oval. He goes, you need to run up to the cricket nets, across to the drama centre, and then down to the red, blue and yellow statues. And you've got to do it in 150 seconds. Ready, set, go. And the kids all take off. They're all taking off. Every second they're running about 3.3 metres. And after 150 seconds, they're going to run 500 metres. Meanwhile, the PE teacher is going to meet them over there because he's going to go, he's not going to run with them. He's just going to go, well, I just have to walk over to the red, and blue and yellow statues. So he's going to travel the velocity vector. He only has to jog, walk 2 metres per second. Right? The boys are off running. They're travelling further, so obviously they have to be travelling at a greater rate, 3.3 every second. But I'm going to meet them over there, so I'm going to move 2 metres a second. And we'll meet there at exactly the same time. So that's one way to show the difference between, and he would obviously travel in a straight line, displacing himself 300 metres west, whereas the boys would travel off on the journey. Okay, and their distance travelled is the magnitude of the journey. Another way of looking at this, you don't have to write this, but I'm just going to zoom in somewhere. Don't write this, just look with your eyeballs. There's an episode of Top Gear that I always go back to explain this. You know how do you guys still watch Top Gear even though it's cancelled? Top Gear with the British blokes.
Oh, driving cars.
Yes, all right. No more talking from Brendan. Often they'll have challenges where they'll need to get somewhere, and it's a race between two of the presenters. And one of these challenges, they started off at this country that looks like a boot in Italy, right? And they needed to get over to Spain, right? Don't write this. Now, Richard Hammond, he got in a Ferrari and he zigzagged all the way. In fact, I'm going to go blue because he zigzagged all the way up through the Alps, through the twisty in this, very expensive car, right? And let's say he travelled 500 kilometres. I'm just guessing that number. It's probably a lot more. And then James May, Captain Slow. Does anyone remember this episode? What did he get in? It was a boat, right? And basically, there's nothing between Italy and Spain. He got in the boat, and once he left the harbour, they just basically went straight line, right? Now, the blue line is Richard Hammond's distance travelled, and the red line could express the displacement. But that's basically what Captain Slow took, and he might have gone only, 300 kilometres. I'm making these numbers up, by the way. Now, point A, point B. The way they edit these competitions is you've got no idea who's winning or who's losing. And they'll often show, as the segment progresses, they'll have a little map and there'll be a little image of a boat slowly moving, and then there's an image of a car slowly moving, and then they've got to get to some little cafe in this harbour town of Spain, this little piazza, and it cuts to James May getting off the boat and running across a jetty, and it cuts to Richard Hammond trying to park his car and running along the cobblestone streets, and we don't know who's winning until they get there and someone would be sitting there with a cup of tea, and then you know that they won because they got there. But for the sake of this example, let's imagine that they got there at exactly the same time and call it, 10 hours. 10 hours it took. In which case, his average speed was 50 kilometres per hour and his average velocity was 30 kilometres per hour. What is my red line missing?
Direction.
Good. So I would have to then, if we wanted to make this proper, we would have to say east 22 degrees north or something like that. Okay, but that's just another way to show the difference between distance, displacement, speed, and velocity. Your car's speedo is only telling you the speed. It doesn't know what direction you're going unless you have GPS. But really, we don't care. I don't care when I'm travelling down Stirling Highway that I'm travelling west 13 degrees south. I don't care about that. I just need to make sure that my magnitude is less than 60 kilometres per hour. Or at 5:30 in the morning, less than 80. No? All right, move on. Okay, now, could you turn the page, I think? Are we up to turning the page?
Yep.
Yes. A yes. Now, if we have small distances and small times, it's convenient to use the SI units, meters, seconds, meters per second. For example, the running activity. You ran 500 metres in 150 seconds. They're pretty nice numbers to play around with. 500 divided by 150. Easy to work with. Larger distances aren't so convenient. You wouldn't say to travel to Busselton on the weekend, you'd have to travel 350,000 metres, and it would take you approximately 12,500 seconds. That's actually how long it would take. But a better unit would be Busselton's 350 kilometres away, and it would take you about 3.5 hours. So for really long distances, we use kilometres, and for really long time, we use metres. Okay? So sometimes it's convenient. If we're dealing with travelling, from one town to another across the country, we're going to use hours and kilometres. And that's what we do, our speed signs. our speed limits are all kilometres per hour because they're a nice unit. Because you can do a quick little bit of mental maths. Okay, Northam's 100 kilometres away and the speed limit's 110. So, I should get there in just under an hour. Or if it's a 50k along Stirling Highway and I need to travel 10 kilometres, it'll take me, I don't know, I'm bad at maths, 10 divided by 50, 1/5 of an hour, 12 minutes. Hey, good at 12 minutes. So we can use that. However, we need to be able to convert. So gentlemen, eyes to the board, please. I'm going to write the following. Kilometres per hour, and I'm going to write metres per second. Elliot, Angus, you haven't written this because your eyes haven't even looked up yet. Write this down and leave a space because we're going to write some stuff in the middle. Okay? Now, we're going to have to do a bit of mathematics. And I want to express I'm going to leave my time conversions on the top of our fraction. Sorry, the distance conversions on the top and the time conversions on the bottom. What do I do to convert from kilometres to metres? What do I multiply by? 1,000. Good. We can times by 1,000. What do I do to convert from an hour to seconds? How many seconds are there in an hour?
60.
There's 60 minutes.
Yes.
So we times it by 60. That gets us to minutes. Then how many seconds in a minute? 60. So we times by 60 again. All right? Now, instead of doing 3 separate things in your calculator, you could go times to convert to meters, convert to minutes, convert to seconds. 1, 2, 3. You can just do it in one conversion. So on this one, I'm going to write, we could times by 1,000. 60 times 60 is 3,600. Right? We can do a bit of cancel. We're actually timesing by 1 over 3.6. That's the conversion. Well, multiplying, the inverse of multiplying is dividing, so that's exactly the same as dividing by 3.6. That's the number, that's all we've got to do. To convert from kilometres per hour to metres per second, we convert to, we divide by 3.6. In this little box here, I would like you to write it now, kilometres per hour, metres per second, and we're going to draw a little flow diagram. We're going to go a little curvy arrow over here, and we're going to write divide by 3.6. And if we want to go the opposite way, the opposite of dividing by 3.6 is multiplying by 3.6. Okay? So that is our conversion. You do not need to show all of the working out. In a question, if you need to convert, all you need to do is go divide by 3.6 equals that many meters per second. Okay?
Why is it a negative?
Meters per second. So remember, kilometers per hour is the same as writing km/h or km divided by h. But I would like you to write it as km h to the negative 1. Okay? Now, everyone remembers 3.6. It's a very nice number to remember. But they forget which way to go. Is it multiply? Is it divide? They forget. Oh, do I time it? Oh, flip a coin. Here's what I want you to remember. If a car is traveling down a freeway at 100 kilometers per hour, we divide by 3.6. And your calculator spits out 27.8 meters per second. 27.8 is around about the length of, what am I drawing here very badly? The tennis court. Okay? It's about the length of a tennis court. So a car on the freeway, every second, they've travelled the length of a tennis court, approximately. Which is why they don't build tennis courts on the sides of freeways, because you've got 1 second to get out of the way if there's a car crossing the tennis court. Okay? And they don't put footpaths near it either. They normally have them fenced away. They don't want little kids playing around because you don't realise it. You see a car, it's off in the distance, but it takes 3 seconds to travel 90 metres. And before you know it, bang, you've been hit by the car. Okay? So that is the correct way. Oop, I was trying to draw a tick. Try that again. Ooh. That is the correct way. The student that does it the incorrect way, 3.6, times by 3.6, 360 metres per second. That's faster than the speed of sound. That's wrong, all right? The cars are not breaking the sound barrier. They're not going Mach 1, all right? When they get on the freeway, they're not going faster than the speed of sound. So just remember that. That's what I do. When I want to convert, it's like, okay, hang on. 100 kilometres is 27 metres per second. How do I get from 100 to... I divide. All right, so kilometres per hour divide by 3.6. Okay? We shall leave that there. Some of you have homework to do. Get it done, and I'll check tomorrow that you've done your homework.